Today we are going to be talking about double angle and power reducer identities. By the end of this video, you should be able to recognize and use the 5 double angle identities, and you should be able to recognize and use the 3 power reducer identities. First, double angle identities are used when you have sine, cosine, or tangent of 2 times an angle. For sine, sine of 2 theta equals 2 sine theta, cosine theta. And you can prove this identity by using the sum identity that we learned about in the last video. If you look at sine of theta plus theta, that's how you would figure out this identity. Similarly, you can figure out what cosine of 2 theta is. Except for this one, there are actually 3 different options. One uses both sine and cosine, one uses just cosine, the other uses just sine. For tangent of 2 theta, you can either use this formula given here, or since we know that tangent of theta is sine of theta over cosine theta, tangent of 2 theta is also equal to sine of 2 theta over cosine of 2 theta. So depending on what information you already have, this might be an easier way to figure that out. Let's take a look at a few examples. In this first example, we are told that cosine of theta equals 5 over 13 on the interval 3 pi over 2 to 2 pi. So let's start by drawing a triangle. We are told that this angle is in the 4th quadrant. We also know that cosine of theta is 5 over 13, and cosine is adjacent over hypotenuse. So the adjacent side over the hypotenuse is 5 over 13. Then you can either use the Pythagorean theorem, or if you know your Pythagorean triples, that means that this other side is going to be 12. But let's think about it. In the 4th quadrant, the x value is positive and the y value is negative. So this side is actually going to be negative 12 because we're in the 4th quadrant. Now we have enough information to figure out what sine of 2 theta is. We know from the identities above that sine of 2 theta is equal to 2 sine of theta cosine theta. We can find sine of theta by looking at this triangle. We know that sine is opposite over hypotenuse, so we have negative 12 over 13, and cosine of theta was given to us in the problem. Then we just multiply all of these together and we get negative 120 over 169. And we can just leave our answer as a fraction. That's it. In the same situation, we're going to find cosine of 2 theta. You can use any of the 3 identities for cosine of 2 theta. I'm just going to go ahead and use the first one, which was cosine squared of theta minus sine squared of theta. Well, we are told that cosine of theta is 5 over 13, and we just figured out on the last slide that sine of theta is negative 12 over 13. Now we can square both of these fractions. And subtract. All 3 of the identities should give us the same answer. If we were not told what quadrant this angle is in, and we weren't positive what sine of theta was, we could have used the identity that only used cosine of theta because that's what we're given in the problem. lastly, we want to find tangent of 2 theta. As I mentioned earlier, if you want to use the tangent of 2 theta identity, that's fine. But we've already figured out what sine of 2 theta is and what cosine of 2 theta is. So tangent of 2 theta is equal to sine of 2 theta over cosine of 2 theta. We know that sine of 2 theta is negative 120 over 169, and cosine of 2 theta is negative 119 over 169. Since we have a fraction divided by the fraction, we need to keep the first fraction the same and multiply by the reciprocal of the second fraction. The 169's cancel out, so we are just left with 120 over 119. And that's it. If you use the tangent of 2 theta identity, you should get the same answer. For our second problem, our goal is to express sine of 3x in terms of just sine of x. We are going to need to use a couple different identities for this. We have double angle formulas, but we are not given a triple angle formula. But I can rewrite this as sine of 2x plus x. In the last video, we learned about the sum identities, so we can use sine of a sum identity to expand this. So I have sine of 2x cosine of x plus cosine of 2x sine of x. Now I can use my double angle formulas to simplify sine of 2x and cosine of 2x. I know that sine of 2x is 2 sine of x cosine of x. And I'm still multiplying by this other cosine of x. And then I know that cosine of 2x, well, I have 3 options. My goal is to only have sine of x in my answer, so I'm going to go ahead and use the identity that only uses sine. So I'm going to have 1 minus 2 sine squared of x. And I still have a sine of x here. So if I simplify this first term, I have 2 sine of x cosine squared of x. And if I distribute, I have sine of x minus 2 sine cubed of x. Now, I need to get rid of this cosine squared. I know from my Pythagorean identities that this is equal to 1 minus sine squared of x. So if I distribute here, I have 2 sine of x minus 2 sine cubed of x plus sine of x minus 2 sine cubed of x. Now I can just combine my like terms. 2 sine of x plus sine of x is 3 sine of x. And negative 2 sine cubed of x minus 2 sine cubed of x is negative 4 sine cubed of x. So now all I need to know is sine of x, and then I can find sine of 3x. So I'm done. Next, let's take a look at our power reducer identities. If we need to find sine squared of theta, cosine squared of theta, or tangent squared of theta, we can do that if we know cosine of 2 theta. So let's take a look at an example. Here, our goal is to rewrite sine to the 4th of x as the sum of first powers of the cosine of multiple angles. That means we don't want any exponents. Well, we don't have a fourth power identity, so let's start by rewriting sine to the fourth. Sine to the fourth of x is the same as sine squared x times sine squared x. So I'm going to use the identities that we just had on the last slide. 1 minus cosine of 2x over 2. Now I need to multiply these together. So I'm going to need to FOIL the numerators. And multiply the denominator. Now I'm going to rewrite this so I don't end up with fractions inside fractions. I said earlier I didn't want any exponents, so I'm going to have to use the power reducer formula again to get rid of this cosine squared. Everything else is going to stay the same. Since I have cosine squared of 2x, when I use the power reducer formula, I'm going to have 1 plus cosine of 2 times 2x, which will give me 4x over 2. Now, I'm going to multiply all of these terms in the parenthesis so that I can get a common denominator. So I end up with 2 minus 4 cosine of 2x plus 1 plus cosine of 4x all over 2. If I combine my like terms, I have 3 minus 4 cosine 2x plus cosine of 4x. And then if I multiply the denominators, that is all over 8. So if you needed to know what sine to the fourth of x was, we now have that formula in terms of the cosine of multiple angles, and we no longer have any exponents.